Welcome to Alienating the Audience, plumbing the depths of both science fiction and science to make your nerd spirit soar. I'm your host, Andrew Heaton, the thinking man's nerd. A few weeks ago, Andrew Mayne joined the program to discuss how to make money on Mars. I enjoyed that show so much that we're returning to the subject of Mars this week. Except this time, we're going to bring on one of our favorite thinkers, Robert Zubrin, to discuss, using our current technology, how we could get to the red planet. And once there, if we found life on Mars, what would it say about the origin of life in the universe itself? Grab a rotating spaceship and some flash-frozen ice cream, and let's go! We're joined today by two people. Andrew Mayne is coming back, author and beloved guest on this program, to help me talk to Dr. Robert Zubrin. Dr. Robert Zubrin is the president of the Mars Society and the author of The Case for Mars and The Case for Space. And Dr. Zubrin, I have decided if I were president, you would be my pick to lead NASA. I'm a big fan of yours.
Well, thank you.
Andrew and I have both gone through the Case for Mars, which I was impressed by the fact that it seems to translate perfectly well to now. I believe you wrote it in 1990, but I was going over it going, it seems to be a good plan to get to Mars.
Yeah, well, the Mars Direct Plan, which is the heart of the book, was indeed developed in 1990, and the book itself was written in 1996 with an update in 2011. But yeah, it was true then, and it's true now.
Right. Can you tell me why you think it's a good idea to go to Mars, as opposed to, say, I know you're critical of the Gateway space station that NASA has proposed. Why would it be better for us to spend our resources to go to Mars as opposed to build the space station?
Well, almost anything is better than building a toll booth in lunar orbit. The Gateway, it's not a gateway, it's a gate. It's a toll gate on the way to either the moon or Mars. But why would it be better to go to Mars than, say, the moon, okay, which is at least a place? It's because Mars is where the science is, it's where the challenge is, and it's where the future is. It's the closest planet that has all the materials needed to support life and therefore technological civilization. It's the Rosetta Stone that's going to let us know the truth about the potential prevalence and diversity of life in the universe. It's the challenge that will make science the great adventure for a whole generation of young people worldwide, out of which we would get millions of young scientists, engineers, inventors, technological entrepreneurs, doctors, biologists. These are the kinds of people that move society forward, and it's the future. It is the world that we can settle. It is the key to humanity's future and becoming a spacefaring species.
Good pitch. Good pitch. And over the course of reading your book, I didn't like you seem very bullish on the prospects that Mars was previously a wet planet and potentially a planet with life, that it wasn't always a lifeless rock, but has lots of water right now, continent-sized permafrost deposits, possible geothermally warmed pools of water underground. So there's biological incentives for us to get there as well, just to see the origins of life in the universe if they in fact happened there.
Yeah, well, when I wrote The Case for Mars in 96, that view of Mars was one that was defensible. It was supported by a fair faction of scientists, but not all of them. Since then, it has been proven.
Okay.
Since then, the Mars Express orbiter, European orbiter, has detected underground liquid water on Mars. The Mars Reconnaissance Orbiter, the American orbiter, has detected large glaciers as far south as 38 degrees north, which is the latitude of San Francisco on Earth. We've detected massive amounts of water erosion features, evaporate features on the shores of ancient seas and lakes. There's no question that Mars was once warm and wet, and that there's still liquid water underground on Mars and vast reserves of accessible water at the surface. In the form of ice.
With the underground water that's there, we know that because occasionally it belches out, and we can see the temporary rivers that result when they pop out of the soil.
Well, yes, we have detected a couple of them. The Mars Global Surveyor, the images collected by the Malin, the scientist on the camera on that, has found a before and after creation of a transitory water flow out of the side of a crater. But the European Mars Express orbiter, using ground-penetrating radar, actually has directly detected liquid water underground.
Got it. Okay. And then on top of that, there is just huge deposits of basically permafrost, or something akin to that, where there's water locked in the soil that we could potentially harvest.
Well, there's continent-sized regions that are like 60% water by weight, which is essentially frozen mud. But there's also actually pure water ice glaciers, massive numbers of them detected by the ground-penetrating radar on the Mars Reconnaissance Orbiter, the American orbiter. And these glaciers contain as much water as the American Great Lakes.
Okay, great. Well,
and they're pure ice.
So you've sold me. Like Mars seems like good interstellar real estate for us to both look for life and to potentially plant some greenhouses and get a foot in the door. So what is your plan to get us there?
Well, my plan that I advocate is known as the Mars Direct Plan, and the way this would work is each mission proceeds with 2 launches. The first and launches of a heavy lift booster with capacity comparable to, say, a Saturn V moon rocket that we used during Apollo. And currently there are 2 such launchers under development. One is the NASA SLS, and the other is the SpaceX Starship. Mm-hmm. The former is expendable, the latter is reusable. They both, though, have capacity in this class. Or you could just re-engineer the Saturn V. But either way, the first launch would send off to Mars a Earth return vehicle with no one in it. And this would go and land on Mars. And in the original Mars Direct plan, I brought some hydrogen with me to Mars to react with the Martian carbon dioxide gas to produce methane and oxygen propellant. Now we know there's available water at the surface, so one could, in principle, go to Mars and make the propellant entirely out of Martian resources of water and CO2, turn that into methane and oxygen. So there's your return propellant. And then once that's done, the next launch, which would be done 2 years later, would send a crew out to Mars. And they just fly out to Mars in a habitation module, comparable in size to, for instance, the habitation module we use in our Mars Desert Research Station in Utah, or the Arctic Research Station that we have. And they fly to Mars in that, land in that, use that as their house on Mars, and explore Mars for a year and a half, and then get in the Earth return vehicle and fly it back to Earth. You leave the habitat behind on Mars, and before you do this, each time you do this, you add another habitat to the base. And so before long, you've created the beginning of the first human settlement on a new world. There is nothing in this that is beyond our capacity.
And if I'm following you, then just to make sure that I've got this, because I'm more of an arts and sciences guy than a sciences guy. You basically, the first step of this is flying an automated kind of self-perpetuating mission that touches down, drops off a bunch of the equipment, and then it sort of fills up its own return tank to Earth, so that by the time we've launched actual astronauts, we know there is equipment waiting for them on Mars that could get them back to Earth. So that's already taken care of.
That's right. So there's a fully fueled Earth return vehicle waiting for them on Mars at the time we launch the crew.
Right.
And this actually makes the mission safer than the conventional mission, in which you're attempting to land in a craft loaded with propellant that you're going to have to ascend in. Because now you know the ascent vehicle has already survived the trauma of landing.
Right. Okay. And then once they're there, because we have separate orbits, and Mars is constantly fluctuating in the distance between the Earth and Mars. I assume that we're trying to land there when the gap between Earth and Mars is the smallest. I assume then that the longer we're on Mars, the bigger that gap is happening. So are they going to stick around for like a full year until it comes back around to the smallest point between us? Or how long would you have the first mission stay there?
Well, you're basically correct. It's just that we're not looking for the smallest distance between us, but the smallest propulsion requirements.
Okay.
Which is somewhat different. But nevertheless, yes, it's a periodic phenomenon that occurs once every 2.2 years. And you get a good launch window to Earth. Good launch window to Mars from Earth, and a good launch window from Mars to Earth. And so, in fact, the way this works is you fly to Mars. It takes 6 months to get there. Then you operate on Mars for a year and a half, at which point the launch window opens to come back, and then you fly home, and that takes 6 months in transit. So it's 6 months out, year and a half there, 6 months back.
Okay, so a fairly long mission for those involved. But at the same time, they've got a year and a half on Mars to look for fossils and see how potatoes grow and all that kind of thing.
Correct.
Okay. I have been told that it would be very difficult because of radiation going out there. That, like right now with the International Space Station, it's within, I can't remember the name of the belt, maybe the Van Halen belt, but basically
the Van Allen.
Excuse me, Van Halen. Yeah, you can see my lack of scientific knowledge. Exactly, the Van Halen belt, the Van Allen belt. Thank you, Doctor. So the Van Allen belt currently shields people that are in the International Space Station from radiation, but that wouldn't be occurring on a long space mission. So over that 6 month period, how do you keep people from getting cancer from radiation, cosmic radiation?
Well, the Earth's magnetosphere. It's not the Van Allen belt. It's the Earth's magnetosphere.
Wait, hold on. I brought up Van Halen, and you just brought up an X-Men character. I feel like there's a double standard here.
Okay. The Earth's magnetosphere shields the space station against solar flares. It does not shield it against cosmic rays.
Oh, okay.
The craft going from Earth to Mars can shield the crew against solar flares as well, using provisions to create a pantry storm shelter, because the solar flare particles are not that penetrating. The cosmic rays, however, you cannot shield against. Either in Earth orbit or in interplanetary space. Although in Earth orbit, we are shielded from half the cosmic rays because the Earth is on one side of the space station, and that indeed does block out cosmic rays. So but the dose rate of cosmic rays at the space station is half of what you would get in transit to Mars. And as a result of that, the fact that we've had a number of astronauts and cosmonauts who've spent a year or more on the space station or on the Mir, which was the Russian space station before the International Space Station, there's about a dozen astronauts and cosmonauts that have taken comparable radiation doses as you would get going to Mars and back, and none of them have developed cancer, nor would we expect them to. The total radiation dose that you would get going to Mars and back from cosmic rays would represent about a 1% risk of getting a cancer at some time later in your life.
Okay.
And while that is not something that one would recommend, for the public, you need to understand the average smoker incurs a 20% risk of getting cancer. So this is actually a small risk compared to that which, hundreds of millions of people simply accept voluntarily because they like to smoke. In fact, if you recruited the Mars crew out of smokers and sent them to Mars without their tobacco, you would be reducing their chance of getting cancer.
Except that they would all murder each other during the nicotine withdrawal. But yeah, good to know. Once they get to Mars, the Martian atmosphere is what, about 1% of our atmosphere? So would we need additional shielding? Because there'd still be a lot of cosmic radiation they'd be exposed to once there, right?
Yeah, but first of all, now you have Mars under you. That blocks out half the sky. So that right there, you're down to space station doses.
Okay.
And then there is a thin atmosphere enough to mask out, first of all, solar flares, and second of all, to cut the cosmic ray dose by maybe another factor of 2. And then furthermore, you could throw sandbags on the roof of the habitat. And that would cut it even more. So the main place you actually get the radiation dose is during transit, not on Mars.
Okay. Once you're there, I think you mentioned setting up a greenhouse. I've seen greenhouse in various science fiction, like The Martian by Andy Weir. The fact that Mars is so much further out, does that like the light is still light, right? So is you could still have viable plants growing there, or do they become less and less viable the further away you get?
You absolutely can. The Martian sunlight is about 40% as strong as Earth sunlight. So Martian sunlight near the equator is about as strong as Earth sunlight in Norway or Alaska.
Okay.
And they certainly have abundant biospheres there, forests and so on. And people, even grow plants indoors with artificial light, which is much lower in intensity than 40% of natural sunlight. Okay. So plants can grow in Martian light. And that's important because if you compare agriculture on Mars to, say, trying to do it on the moon, first of all, the moon has 2 weeks of light, 2 weeks of dark. Plants generally want the 24-hour cycle, which you do have on Mars. The Martian day is almost the same thing as the Earth day. Mm-hmm. Second of all, there is no atmosphere on the moon, so you would have to shield the plants against solar flares. You either have to use artificial light, which is extremely energy intensive, or very thick glass greenhouses, which would be very difficult to construct. On Mars, the atmosphere is as thin as it is thick enough to mask out solar flares. So you could have thin-walled greenhouses on the Martian surface and growing them in natural light.
Great. So then the only real concern then is just having walls thick enough to maintain from dust storms and just kind of terrestrial features, but it would be sufficient.
And to hold some pressure.
Right. Yeah. Okay.
Would you mind if I interject here too?
Yeah,
Dr.
please.
Zubrin,
I'll throw this out. Andrew, you're smarter than me, and you know more about this than I do. So please feel free to jump in as much as you want.
Both of those are very questionable prospects. One, could you address maybe for our listeners to kind of like people like they see movies with, let's say, Martian dust storms and stuff, and they have this very dramatic idea, but like the reality of something like that per se on Mars, and I also like to talk a little about the geography too.
Okay, well, all right. So first of all, let me just say, in terms of the movie The Martian, of course, this very powerful dust storm was a key plot element. And that was not realistic, although, any movie is going to take liberties, with science. And The Martian actually, frankly, was rather unique among Mars movies in taking the fewest. Mm-hmm. The spirit of The Martian is realism as opposed to fantasy. And essentially that makes it the first real Mars movie. The previous ones were basically shoot-'em-ups or horror pictures. But that said, that dust storm was unrealistic. The Martian atmosphere is 1% as thick as the Earth's, and so the wind velocity on Mars, it would take 100-mile-an-hour wind on Mars to have the same force as a 10-mile-an-hour wind on Earth. And while you do sometimes get 100-mile-an-hour winds at altitude on Mars, we've yet to see them near the surface. The Viking landers survived years on Mars. The Spirit and Opportunity survived years on Mars. Curiosity has survived years on Mars. So that's not going to happen. If you were trying to land through a dust storm, so now you are a wind-dominated object because you have this big parachute out there, then the wind could take you and crash you. And that, I think, actually happened to a Soviet Mars probe in 1971. But if you're actually on the surface, no, they don't represent the hazard. They do represent a problem in that they block sunlight. Not block it so much that you can't see, but block it so much that solar panels would produce negligible electricity. And this is one reason why we really want to have a nuclear power plant for use at a Martian base. So we have reliable power regardless of a dust storm. But in terms of as a threat to surface structures, no.
One of the things that people kind of get fixated on is we see the images that come back from the surface of Mars, which are fascinating, but we tend to put landers where it's best to land things and we can have rovers go around on. And we don't see some of the more dramatic landscape and geography of Mars, and let alone the subterranean stuff yet. Mars is very likely riddled with lava tubes and riles and other structures. Can you talk a little bit about that, the subterranean part of Mars and some of the other things that we have yet to sort of get a closer look at?
Yeah, sure. Most of Mars is underground.
It checks out. It checks out.
Yeah, it's kind of like the ocean. Most of it's under the surface.
Yeah.
And so there's a lot to discover there. We've done some very crude exploration underground with long wavelength ground penetrating radar from orbit. The way ground penetrating radar works is the longer the wavelength, the deeper you can go, but the less your resolution. Okay. In other words, that you can only see feature. If you have 10-meter radio, this feature has to be about 10 meters thick to see it. You can't see a 1 meter thick feature with 10-meter radio. But on the other hand, with 10-meter radio, you can go 10 times deeper than you can with 1 meter radio. I'd like to see a lot more ground penetrating radar work done at a multitude of frequencies, ranging from half a meter to 20 meters. And you can generally get down maybe 10 wavelengths. And so we should be able to see lava tubes. It was with these sorts of radars we were able to see these glaciers and these lakes. But in general, these have been longer wavelengths. But certainly lava tubes are believed to exist on Mars. In fact, I've spoken to some scientists who believe that they've detected underground caverns. So that would be very interesting. Of course, the other way to explore underground is drilling. For this, you really need to send humans to Mars. And from a strictly scientific point of view, you really have to do this, because the place where you're going to find extant life on Mars is underground, not at the surface. The surface is bathed in ultraviolet light, which is fatal to microbes. You've got to get underground, and furthermore, underground is where the liquid water is, which is essential to metabolism. Now, of course, with rovers, you might conceivably find fossils on the surface, because there was once liquid water on the surface. Although, as fossil hunters, rovers are far, far inferior to human rockhounds. Mm-hmm. There's no comparison. But it's at least possible you could find it with rovers. But underground, you can't drill with these rovers and so forth. You really need people. And then furthermore, you're going to want to bring up the water, and you're going to want to subject it to biochemical and other forms of examination to see if there's organisms in there and what they're like. And to me, this is the essential question, because, see, I actually am pretty sure that there was once life on Mars, and probably still is. And the reason why I have a very high certainty of that is because we get transport of Martian materials to Earth all the time, and right. Mars gets transport from Earth. And this was emphatically the case during the time 3 billion years ago, when Earth was already covered with microbes, and it was being bombarded by meteors at a significantly higher rate than it currently is. And so Mars would have gotten life if from no other source than the Earth. Similarly, it's quite possible that Earth got its life from Mars, right. Or that both got their life from an outside source. This is the real mystery. You see, here's the thing about life on Earth. Life appears on Earth virtually as soon as it can. Okay, there's no evidence that the Earth was ever habitable and sterile at the same time. As soon as the heavy bombardment ended, we have microbial life on Earth. Now, that means one of two things. Either life originates from chemistry spontaneously, very quickly, in which case life should be expected everywhere. Or life is already floating around in space, and as soon as a planet becomes habitable, boom, it becomes inhabited. And there you go. Now, so the question is not, is there life on Mars, but what life is there on Mars? If all life on Earth has a common origin. It all uses RNA and DNA. It uses the same alphabet to do genetic information. Okay, so it's like we know that the French alphabet, the English alphabet, and even the Polish alphabet, they all have a common origin in the Latin alphabet. Okay, there's no possibility that they originated independently of each other. Okay, the Russian alphabet is different, but it has a number of points of similarities, which point to a common origin further back. The Chinese alphabet, on the other hand, has no similarity. It doesn't even work on the same principles as the Latin or Cyrillic alphabets. It is a completely separate genesis. Okay, so the question of life on Mars, does it have the same genesis? Does it use the Latin alphabet of RNA and DNA? Does it use a Cyrillic alphabet that indicates a sort of a common origin with Earth life, but maybe the two of them are descended from something else and they split up further in the past? Or is it Chinese? Okay, and if it's Chinese, that suggests a completely separate second genesis. And that would suggest that life in the universe has enormous diversity because it has widely separate, diverse information systems. Now, on the other hand, if what we find on Mars uses not just the Latin alphabet, but English, as it were, then they were clearly seated in common. To me, if it's identical, in other words, if we find E. coli on Mars, and not just RNA and DNA, that would say that they were literally seated in common. And also, here's the other thing. There's a mystery about life on Earth, which is that we find no free living forms that are simpler than fully developed bacteria, and which are by no means simple things. And so this suggests that life on Earth is an immigrant phenomenon, that it came here already developed, just like you don't find any features of Western civilization in North America that are more primitive than the Renaissance, okay, because it's an immigrant phenomenon. Okay, we don't find Bronze Age Minoan artifacts in North America, okay, or Roman stuff or whatever. Or it begins in the Renaissance and it came here, and so that makes life on Earth look like an immigrant phenomenon. Now, if we go to Mars and find RNA and DNA life similar to Earth life, but also more primitive representatives, that would say that Earth life came from Mars, because you would see the previous evolutionary history, just as we can tell that the mainstream American culture came from Europe. But because we can go to Europe and find antecedents to Renaissance artifacts. Okay. So we really have to go to Mars and not just look at fossils. We have to look at life. We have to be able to see what its information system is. And this is going to tell us what's really important.
Is there a way to determine the probability of whether life is still there or not? I mean, you mentioned earlier there's liquid water in or there's liquid water heated by geothermal. We think there's potentially caverns there. So it's possible that life has clung on. Is there any way to figure out whether it's more or less likely?
If you ask Spock any question, he'll tell you the odds are 1,472.6 to 1. But in fact, of course, there's no way to calculate such probabilities. However, I think it's very probable because, for example, the earliest life forms that inhabited the Earth can no longer live on the Earth's surface because it has been, from their point of view, polluted by oxygen from photosynthetic organisms. It is not habitable. And so when the Earth's surface became uninhabitable to its earliest life, they went underground, and they're still there. After 3 billion years of hiding out while, looking up, and there's, trilobites and dinosaurs and mastodons and the Wehrmacht and all tramping around.
Crazy year.
We've seen them come, we've seen them go, and in fact, they'll probably be here after life on the surface of the Earth becomes extinct. But so I think if life could have ever existed on the surface of Mars, it would have retreated with the water and maintained itself in whatever habitable environments remain to it.
So as far as the sort of the life that we could find there, and I think, one of the things would probably be the first things that would have made it to there or from there to here would have been like lithotrophs, things that like to live in rocks and stuff like that. Do you think, was there enough time for multicellular life? Was there enough time in Mars's history to get to more complex forms of life?
Well, opinions on that differ. If you take Earth as the example, okay, and if you assume, that life landed on Mars, say from interstellar sources, which I actually think is what happened, that Earth and so if I'm right, we will find life on Mars, and it will use RNA and DNA. That will be the proof. If you find life on Mars that uses a different system, then there is not interstellar panspermia. Because, but if we find no life on Mars, then there is not panspermia. So my hypothesis is falsifiable. But the question is this: if you just look at the clock the evolutionary clock of Earth, you would say no. That multicellular organisms followed the evolution of eukaryotic cells, which didn't happen until maybe 2 billion years, and then it took another billion years to get multicellular. Although there are some multicellular bacterial forms, but they're not what you would ordinarily think of as multicellular life. Okay, but there's a theory that's been advanced by Chris McKay, who's a NASA scientist at NASA Ames, who thinks that this clock is a function of the oxygen in the atmosphere. That is, if Mars could have been oxygenated early, then it could have evolved faster. And in which case there could have been enough time.
Interesting. Can we talk about the panspermia idea?
Yeah, I
saw
wanted to go back to that.
Years ago. There was a paper from some Japanese researchers that talked about if you took the impact event that we had 65 million years ago and you extrapolated the amount of Earth debris, how far it would have gone. I think they said something like a sphere of like 100 light years or something that Earth could have spread life to as far as, and if you roll that clock back to other stars and other things, and the fact that, the galaxy and solar systems are way more dynamic than we realized between rogues and all the objects coming in and out. We're now aware of that. Now we're looking at, interstellar comets and stuff. Let's talk a bit about that. Like, how far back could that go? And
well, okay, I published a paper about a year ago in the International Journal of Astrobiology, in which I presented calculations showing that these, and it's really rather straightforward. You can see that the sun and other stars would have if they're moving randomly at velocities of around 10 kilometers a second with respect to each other, that's superimposed on the general galactic rotation, which is 250 kilometers a second, that you're going to have close passes, that is, passing through our Oort cloud and us passing through their Oort cloud about every 20 million years. And this would precipitate bombardments, which interestingly corresponds with the typical frequency of mass extinctions on Earth, which is not a true periodic phenomenon, but it has a characteristic frequency. And not only that, you're being bombarded and therefore spreading material exactly when another solar system is nearby. And furthermore, in many cases, they're being bombarded not by parts of their own Oort cloud, but by parts of our Oort cloud. That is, their sun is passing through our Oort cloud. and we're passing through theirs. So the things that are impacting us are actually not just our own Oort cloud objects being destabilized, but actually, for the most part, Oort cloud objects from another solar system. And so the analogy I give is, if you consider warships in the age of fighting sail, that with their sails, they had global reach, they had unlimited range, but their cannons could only fire a few hundred yards. But they only fired their cannons when they were close to each other. Okay, so they're not just firing cannons randomly. How could they ever hope to hit another ship? The answer is they're sailing all over the place, and they fire the cannons exactly when they're close by. Okay, and similarly, the bombardments are taking place exactly when the other solar system is close by. And then if you say this is happening every 20 million years, and 4 billion years, that's 200 such encounters in the Earth's history. So the Earth, there's been life on Earth almost 4 billion years, 3.7 billion years. So we've been wandering through the galaxy, spreading life all over the place, that is emitting material that has bacteria or other microbes on it probably 200 times in the past 4 billion years. And similarly, other stars, this sort of thing's going on. Now, so if one out of those 200 encounters resulted in us seeding another planet, you would have a critical reactor, if you understand. Like in fission, when a neutron hits a uranium atom and it makes 2 more neutrons, if one of those hits another, then a chain reaction is sustained. If average more than 1, that is, if 1.1 is the average, then it multiplies exponentially. Okay, this is, of course, the COVID-19 problem. Can we get R naught less than 1? Because if it's greater than 1, it expands exponentially. If it's less than 1, it declines exponentially. So I view the galaxy as a critical reactor. I'm pretty sure, or I find it very difficult to believe, that if we've had 200 chances to have spread biological material into space, that several of them have not struck home. And so if the Earth has, for instance, inseminated 5 other planets, and if the average living planet inseminates 5 other planets, then it doesn't seem very hard to see that there's going to be life all over the place.
That's absolutely mind-blowing. So we could 500 years from now, we could get to Alpha Centauri and find life there with DNA and RNA that either we originated from or vice versa.
You can even the other side of the galaxy. 15 times since life has been on Earth, the galaxy has spun around. I think. Correct me if I'm wrong
and
on
Alpha
that.
Centauri is only the closest star at the moment.
Right.
Yeah.
Okay.
And it's 4 light years away. But every 20 to 25 million years, another star passes within a couple of tenths of a light year of the sun.
Right. So we're changing in relation to other stars in the galaxy. It's not a constant. Right. In the same way that our solar system is not a constant. The bodies within them are operating at different speeds.
Right. Well, there's a general speed which is going to be quite similar. Of this, for instance, at our distance from the center, 250 kilometers a second. But there is, within that general crowd motion, there's random motion. It's like you're walking in a crowd of people, and the crowd is all moving forward at a certain rate, but nevertheless, people are bumping into each other because they have a certain amount of random motion within the crowd.
Do you have a take on Fermi's paradox then? Because in the hypothesis that you just laid out for us, the universe should be teeming with life. How come none of it's sending us sitcoms or anything?
Well, I don't know about sitcoms, but my answer to Fermi's paradox is that they're here. It's us. We've met the aliens, and they are us.
Right, we're the immigrants.
Now, furthermore, now, if you look at interstellar travel, if you think of it in terms of starships, this is a very energetic proposition to try to get massive objects, 1,000 tons at minimum, maybe 10 or 100 or 1,000 times that size, up to velocities of several percent the speed of light. You're talking gigantic amounts of energy, equivalent to several times the total energy production of the Earth annually to just move one ship. And you can say, well, a couple hundred years from now, we're going to be so much richer that that'll be affordable. Okay, but there's easier ways to spread life. And I've got a paper on this. It's called Interstellar Communication Through Microbial Data Storage, or through microbes. It's online somewhere. And if we wanted to make panspermia happen, it'd be very easy to do. We could make what I call micro sailcraft, which would be a few microns in diameter, have a sail about a micron thick, have a payload about 4 microns in diameter containing microbes that have genetic code to replicate our biosphere. And solar light pressure would send these off into interstellar space, and not at relativistic velocities, but at velocities of like 30 kilometers a second. They'd reach other solar systems in tens of thousands of years. We could provide within a few microns sufficient shielding to block against ultraviolet, which is the main hazard to microbes, not hard radiation. I think this is a more effective means of communication than radio. The SETI program is founded on this paradigm that was laid down by Frank Drake and Carl Sagan, of that, they'd be broadcasting, and they're going to use radio, and they want to alert us to their existence, so they'll broadcast, mathematical truths like the value of pi or the Pythagorean theorem, and then you can detect that, and then you respond, and it's kind of like a Freemasonic handshake. Okay, hey, we know about pi, you know about Pythagoras, let's get together. Here's the plans for starships, and so on. Now, it's hard to see the adaptive value of such communication. It's hard to see also, frankly, if you simply calculate the amount of energy required to send data at significant data rates across interstellar distances, you're talking about big equipment with gigawatts of power, and you'd have to, for instance, let's say they detected that there was oxygen in Earth's atmosphere, which they could with telescopes and spectroscopes. Okay, so, there's life on Earth. Let's transmit them a signal, see what they have to say. And, the early amphibians do not reply, because they didn't use radio. And neither did the dinosaurs or the mastodons or the trilobites
or the Wehrmacht.
The Romans. So they'd have to have a great deal of patience to keep this program up. But First of all, what kind of communication do we do with people that we don't know? Propaganda.
Yeah.
Okay. Think of Radio Free Europe or Radio Moscow or the Gideons. Okay. And the message is, be like us. Okay. We are good. Be like us. We'd like you to become us. We'd like you to join the free world. We'd like you to join the Christian church. Be like us. Now, the Gideons have a more efficient way of transmitting information than Radio Free Europe. Radio Free Europe's got to transmit every day, and it's got to hope that the people that it's listening to are listening to it's broadcasting to, are listening to the frequency, and they got radios and all this kind of thing. Gideons, they put a Bible in the hotel room. Okay, and it stays there. And they don't have to be broadcasting into the room all the time. And so microbes sent across interstellar space can be done with very little energy. They can carry a great deal of information. But is the information of the form, here's the value of pi, here's our dictionary, and here's the plans for starships? Or is it be like us? In other words, hey, why don't you try chlorophyll? How about central nervous systems, backbones? We got some ideas on how you should evolve. Boom, we'll throw it into your biosphere. Okay, in other words, if the transmitter if the message is in genetic form, the receiver should be in genetic form. And it's not, here's the plan for starships, it's here's the plan for backbones. And so I think if we're going to find ET, we need to look in the genome.
Brother, have you heard the word about rhodopsin? It's a really good protein, can do some cool things. That was my issue, kind of the Drake equation. As a kid, I liked it, but I always said, man, there are two big assumptions there. One, intelligent life that wants to communicate, intelligent life capable of communication, and then they all become Jehovah's Witnesses and decide they've got to spread the word to everybody else, which was, the kind of the leap as we make these assumptions that, life at that form is going to be just like us and is want to communicate like.
Well, here's the thing about that. I think life forms that send the message be like us are likely to be much more common than life forms that don't send such messages. Mm-hmm. Okay, it's the reason why there are more Christians than there are Jews, even though there were Jews first. Mm-hmm. Okay, because the Christians are seeking converts.
Right.
Okay, and the other big religions, Islam and Buddhism, are also religions that seek converts. Religions that do not seek converts have much smaller numbers of followers.
Yeah, that makes sense.
With your microbial cell model, Doctor, I'm thinking something that's 4 microbes, in width and 2 microbes of cargo. When it hits the atmosphere of a planet, why wouldn't it just burn up? How would it get from space through the atmosphere to the surface to replicate?
Okay, so those are microns
Excuse
dimensions.
Me. Yeah.
Okay, because it has a very low ballistic coefficient. You can actually do the calculation, and you can see that things that are have very little mass per unit area, when they hit an atmosphere, they can slow down with very little heating.
Okay, fantastic.
It's kind of like the small versions of like why raindrops don't burn us when they fall, several miles down and pick up velocity because it just,
Right.
So, another approach I think is pretty interesting. I'm friends with Dr. Phil Lubin, and his lab's been working on using like phased array lasers and stuff to use laser or photonic propulsion to move small payloads, with the idea of that would be another approach, because if you had Bill Gates level money right now, you could build a phased array and you could probably send small probes, to Alpha Centauri within the next 10 years or so using an approach like that. And, it's a bigger
that is true. But if you take like the Breakthrough Starshot mission, mm-hmm. Okay, if you were to look at that and say, what part of that is possible to do right now? Well, the Graham-sized spacecraft, if they put out a $20,000 prize, probably some kids at MIT would make one within a year. The solar sails that are micron thick, once again, is a doable thing. But they need a megawatt space-based laser. Mm-hmm. That they don't have. And now I've made the suggestion to them, and I discussed this briefly in my book, The Case for Space, that they should just do the first 2, and they could send a probe to Saturn and have it get there in a year. In other words, it wouldn't have an interstellar velocity, but it would have a hell of a velocity for as a solar system probe. Mm-hmm. But yeah, if you had lasers, you can make things go faster. They'd have to be very powerful. But if you just wanted to, spread your genes, spread your oats through the galaxy, it seems to me the cheapest and most effective way is to use the power of your star.
Well, that's also, I think, an approach that is more, like I said, replicating, but also is that if some of these probes were designed when they encountered other solar systems to take some matter and make them into other probes and stuff and wait for the solar winds or whatever and to be able to escape the heliosphere there, et cetera. So that's it makes it easier to leapfrog without even having to go, make terrestrial landing in some other places too.
Sure.
from your approach.
Mm-hmm.
Could you answer a question too? Like I've heard speculation about that the Viking lander, that some of the data that it came back with was actually more indicative of life than we thought, and that looking back on some of what the results were, that there was a case that we needed to send better instrumentation or whatever, or we didn't quite understand what we were looking at. And what's your opinion on all of that?
Well, that's true. The Vikings landed. They had 4 experiments. And 3 of them gave the signal that would be in agreement with the existence of life. And 1 of them gave a signal that would say that there wasn't any life. And so it has contradictory results. And, the Gil Levin, who's the principal investigator on one of them, known as the labeled release experiment, one of the experiments that most forcefully argued for life, has continued to maintain that his experiment showed there was life. But this shows the limitations of robotic probes with a fixed repertoire of experiments that they can do. If you had human investigators there, we could have gotten to the bottom of that straight away.
So on that subject, the planetary protection protocols, I think we're all for let's go to Mars, let's go do it. But there are people that are saying, hey, let's wait an indefinite period because we don't want to affect life there. And I think even if there wasn't, there are going to be people who are going to argue, like, let's not ruin the rocks. What's your take on that?
Well, it's a nonsensical point of view. Okay, first of all, the planetary protection breaks down into 2 versions. One is the back contamination threat, which is the argument that we will get diseases from Mars, and so we have to watch out for that. And the other is the forward contamination issue, where you have people saying we don't want to send people to Mars because we'll never know if the life we find there is something that was there or something that we brought. Okay, so let me, because the back contamination thing tends to make the headlines, and it's the sillier of the 2. There's no place on Earth that you can go that you are not infinitely more likely to find a pathogen than on Mars. Because there are no macrofauna or macroflora on Mars, and it is impossible, therefore, to propose a life cycle for a Martian pathogens because there's nothing there for them to live on. So the idea, pathogens coming from Mars is ridiculous. And certainly, we don't quarantine archaeological digs, even though we know that at the time of the pharaohs or the Middle Ages, there were various epidemics, or paleontological digs. There certainly were pathogens around when the dinosaurs and so forth were around. And frankly, if you're a gardener, you easily can dig to the level of the 1918 flu epidemic. People do it every day, and we don't quarantine them. So that's just nonsensical. Now,
what if they didn't have RNA, DNA, would we necessarily be able to predict how Martian life would react with ours? Like, what if non-DNA hits us and it just eats our DNA or something?
Well,
like a prion.
Okay. Well, the other point is that the Martian life, if there is any, has already been here, and it gets here all the time. Because we have natural transport of material from Mars to Earth all the time. We get about 500 kilograms of Martian rocks landing on Earth every year. The Allen Hills meteorite, which was very prominent in the news back in 1996, because there was phenomenon in it which some people argued was evidence of life on Mars in the distant past. Now, the jury is still out.
This is the one from like 98 that they found in Antarctica that looks like in
96.
Yes. Yeah, 96 is a black and white photo that looks like a bunch of worms.
Yes.
Okay.
That's it. Now, the importance of that meteorite, as far as this discussion is concerned, is that it was very thoroughly examined. And in consequence of that examination, it was found that large portions of that rock were never raised above 40 centigrade during their entire history of ejection from Mars, flight through space, re-entry, and landing on Earth. So that rock was never sterilized. If there had been life on it when it was on Mars, it could have made it to Earth. And so we get that we've had trillions of tons of this stuff landing on billions of tons landing on Earth since 3 billion years ago. And so if we could have gotten the Red Death from Mars, we already have.
Good to know.
Okay. So now we have the forward contamination issue, which is more respectable, but equally false. If you went to Mars and you discovered life there, how would you know that it was there before you? Well, how do we know there was life on Earth before us? Okay. Of course, we can find out there was life on Earth before you and me from our parents, but in terms of as a civilization, we found out that there was life on Earth before there was people from fossils. And if there was life on Mars before you landed there, it will not only be there in its present form, it will have left fossils and other biomarkers. In other words, if it was there before you, by definition, it was there in the past. And you can look at the past and you will find out if there's evidence it was present there. And if there's no evidence that it was there before you were there, it means it wasn't there before you were there. And that's all there is to it. Now, in addition, if it's any different than Earth life, obviously you didn't bring it, but even if it's the same as Earth life, you still have the discrimination of, is there evidence that it was there in the past? In other words, if there's bacteria on Mars, it's not that there's 5 or 6 on a rock near your landing site and none anywhere else. Mm-hmm. Okay, if it was there before you, there were trillions of them there before you, and their bodies are still there to be found. So to me, this idea that we would not know that there was life on Mars in the past, if it had been, is like the creationists who say, how do you know that the Earth was not created with the fossils in it? Evolution, no evidence for that. Because God could have just made the Earth with fossils.
Yeah. Well, I guess there's the other argument, too, though, that to do anything to it, I don't know, not to disparage like the Sierra Club, but sort of that mentality of like it should be pristine by itself and that we shouldn't, have any impact on it or whatever. And, and I'm kind of a manifest destiny kind of person. I'm like, if it's there, let's use it.
Put a flag on it.
Well, also, I think that is a crazy argument on their part. Because if you ask the Sierra Club, or an oil company executive for that matter, or anyone in between, what do you think of the idea of taking the Earth as it is now and transforming it to something like Mars, where, it's just a desert with maybe some bacteria in the groundwater? Wouldn't that be swell, and get rid of all these rainforests and pine forests and coral reefs and other stuff and used bookstores and all the rest, and just have a nice red desert, with pristine basaltic rocks lying around here and there. And, they said, you're nuts. Okay. You're like totally nuts. Okay. Well, all right. If we can all agree that would be a very bad thing to do, can't we then all agree that if we could take a planet that is a dead red desert and turn it into a living world, that would not be a profoundly good thing to do? Okay, if you can make an environment worse, you can make it better, by definition, unless you simply are arguing that humans are guilty and whatever they do is wrong. Okay,
space Calvinism. Humans are always bad.
Whatever they do is wrong. Okay. There's no logical consistency to that argument other than hatred of humans.
Well, on that note, how what is the possibility of eventually? Let's say we go with Mars Direct. We've now got a foothold on Mars. We've got, over the course of several successive missions, we've now got 6 or 7 linked habitats that are there. So we've got kind of a Martian village. We've got greenhouses. 100 years later, it's self-sufficient, or a few years later, self-sufficient. Is it possible to terraform Mars, noting that there's only 1% of the atmosphere? If you warm up the water, I assume it just kind of floats away.
Well, no. If you warm the water and kept it warm, it would be liquid. Yeah.
Okay.
Float away around the planet, but not float.
Right. No, not float. That's so. If it's only 1% atmosphere, it's still like you got to figure out the atmosphere to make it terraform.
Well, you got to thicken the atmosphere. Now, look, my preferred proposal for terraforming Mars makes use of a technique that we're currently perfecting, known as global warming. That is, if you put greenhouse gases into the atmosphere, you can warm a planet. Okay, we're demonstrating virtuosity at that. And but if we really wanted to do it, as opposed to doing it by accident, there are very powerful greenhouse gases that we could make that are far more powerful than carbon dioxide or methane. These, for instance, are fluorocarbon gases like CF4, thousands of times more powerful greenhousing agent than carbon dioxide. And if you produce these gases at a rate that comparable chemicals are currently being produced on Earth, these general family of chemicals are used as refrigerants. But didn't put them in refrigerators, you just released them into the atmosphere in order to warm the planet. You would warm Mars by 10 centigrade in 50 years. Now, that's a lot. If you look at the global warming on Earth since 1870, when industrial civilization became significant enough to matter, it's 1 degree centigrade is the global warming in the past 150 years. So this would be 10 centigrade in 50 years. So that's 30 times as much warming, and it would have a very strong effect. It would cause massive amounts of carbon dioxide that are soaked into the soil to outgas and thicken the atmosphere. And then CO2 in those concentrations would be a very, very strong greenhouse gas. And you'd warm the Mars by perhaps another 50 centigrades, and which is vastly more than anyone is hoping or fearing will happen with respect to the Earth. And so now you've got a much warmer Mars, and the ice and the permafrost will melt, and the rivers of Mars will flow again, the lakes will fill again, there'll be rain. And on that Mars, you could start spreading plants, and they could make oxygen. Now, if we're talking about the kind of plants that we're familiar with today, and you actively help spread them across Mars, it would take about 1,000 years to produce enough oxygen for people to breathe. Somewhat less for some other, insects and so on. But but if we're talking about a project that's happening, not even starting, say, for 100 years from now, and not into full swing for 200 years, it's hardly visionary to assume that there won't be genetically modified plants with a much higher efficiencies of photosynthesis than natural plants or close to natural plants that exist today. And this could greatly accelerate the process. Or other genetically genetic modified organisms, basically nanotechnology. And, the potential of this is enormous. And I don't talk about nanotechnology in my books because at this point it's magic, other than in the form of biotechnology. But what's magic to us is not going to be magic 100 years from now. And I think that Mars will be terraformed. I think Mars will be terraformed not in 1,000 years, but in less than 200 years. And Here's what I think. I think that 200 years from now, somebody going into the university on Mars and checking out The Case for Mars out of the library, because it will be there, and they read it, they'll say, wow, this is really something. Okay, here's this book written in 1996, and he's talking about terraforming Mars. Imagine that. But doing it with fluorocarbon factories and green plants, how 20th century can you get? It's kind of like, you read Jules Verne's book, From the Earth to the Moon, and it was written in 1865. And they launched from Florida. It was a crew of 3. They traveled in a capsule. It orbited the moon. It landed in the Pacific Ocean and was picked up by a United States Navy warship, all as actually happened 104 years later. Okay, but the motive force was heavy artillery. And so, he got an awful lot of things right. He even figured out where the launch site would be. But heavy artillery, that was, he was a 19th century mind grappling with a 20th century problem. And similarly, I'm a 20th century mind grappling with a, 22nd century problem. So I'm not going to be aware of certain tools that they're going to have at their disposal. But the fact that I can conceive of this in general terms, to me, is an existence proof that it'll happen.
Is there sufficient raw material to make CFCs on Mars, or will we have to because I'm thinking if we have to transport them from Earth, that seems like a really big problem logistically and cost-wise.
I'm sure there is. I mean, fluorine's very reactive. There's no reason if there was ever fluorine in Mars's elemental composition, it would still be there because it would react with things to form salts, and rocks, and things.
Okay.
One of the things I think that a mindset I think that we should shift from is that sometimes people think about it's like we go to Mars, we put a bunch of people there, then that's it. Kind of the idea we colonize, and then that has to be self-sufficient. And I'm like, Singapore's not self-sufficient. You don't have to be this totally independent Mars. Is if you're having, like Elon Musk wants, fleets of spaceships going there every synod, and you're going back and forth, it becomes part of the Earth economy and part of kind of the solar economy, hopefully. And kind of, could you talk a bit about that idea? I know you've talked to Elon about his plans of like, let's build a ton of ships and let's just keep going back and forth.
Right. Well, certainly Mars won't be autarkic. And it would be a tremendous disadvantage to Mars to have to be autarkic. The poorest countries of the Earth are those that attempt or are forced to be autarkic, North Korea, and so forth. But you don't want to have to bring to Mars bulk materials. That is, things that can be made on Mars that are massive: steel, oxygen, food, plastics, glass, so forth. Make them on Mars. You only want to have to bring to Mars, higher value things, which are things
iPods, iPhones, yeah.
Yeah, iPhones, exactly.
Yeah.
Or if you think of them, you don't want to bring food to Mars. You don't want to bring the glass for the greenhouse to Mars. You don't want to bring the pipes for the greenhouse to Mars. But maybe you bring the chips for the control circuits that do the automatic control of the pumps in the greenhouse.
Kind of like the United States is. That's one of the arguments I make is like we can't produce a lot of the things that we use today because that manufacturing happens elsewhere where it's more cost effective to do that. And it's sort of the myth of autonomy. Right.
To the extent that something has low value per unit mass, it is less attractive to transport it.
Mm-hmm.
And this is, of course, more true if you're on Mars than another continent on Earth. So now the question then is, what will Mars export? I believe that the key export from Mars is going to be intellectual property, and because there's nothing easier to transport across interplanetary distances than information. And the highest value information that there is a patent. And so you know, a megabit can be worth $1 billion if it's a patent. And that can be transported from Mars to Earth currently in less than a sixth of a second. So, but why would there be inventions on Mars? I believe that there'll be inventions on Mars because the Martian population is going to be a technologically adept group of people in a frontier environment where conditions are going to force them to innovate and where distance from the home world are going to free them to innovate. If you look at the history of America, it's a very incisive essay that was written in 1892 by Frederick Jackson Turner. It's called The Influence of the Frontier on American History. And in it, he discusses how the existence of the frontier affected the American mentality. And once again, the frontier was a place where people were forced to innovate and free to innovate, and also where there was a severe labor shortage that drove things in the direction of, well, for example, labor-saving machinery, and also freedom from various forms of bureaucratic or customary red tape, as it were. For example, today, if a woman is a school teacher, we don't think of her as some kind of feminist icebreaker. It's accepted as sort of a normal profession for women to have. But this was not always the case. It is typically up through the mid-19th century, the school teachers were ministers. But on the frontier, with a severe labor shortage, if you had a girl who was literate and knew arithmetic, so by God, have her be the teacher. And then this, having been proven at the frontier, propagated eastward during the Civil War when you had a labor shortage back east. And it's now accepted as perfectly normal. It's kind of a Rosie the Riveter phenomenon, if you will. And it's also, for instance, black people. The freed slaves, of course, the worst place to be was to stay in the South. Going north was better, but going west was better still. Because, once again, if you could do something, well, we need people who could do that. So a labor shortage, tends to be a good thing for the worker. It means pay is higher, and it means that artificial restrictions that would limit what someone could do with their talent are lifted. So there's going to be nothing in shorter supply in a Martian settlement than labor power, both in terms of quantity and diversity. So yes, you'll have the same drive for labor-saving machinery that you had on the American frontier, but also more advanced versions of it, robotics, and artificial intelligence. And artificial intelligence is a way to expand your workforce in its diversity because it gives you the talent to do certain things that you can't do right now without it. It makes you an expert at something that currently you're ignorant of, and so on. So I think the Martians are going to make great advances in these areas. I think they're going to make great advances in genetically modified crops because they're going to be doing greenhouse agriculture with very limited acreage. They're going to want maximum productivity. They're going to, maybe it'll be the Martians that bring fusion power into existence because they won't have the option of fossil fuels. Yes, you can make fossil fuels on Mars, but you need an energy source to do it. But there's deuterium on Mars. This kind of thing. So I think that these sorts of inventions made on Mars will be licensable on Earth, and they will generate income, which can be used to buy the necessary imports.
And some of those innovations, too, that we get in frontier situations where we have expansion are things that we just take completely for granted, like the Sears Roebuck catalog. You had people in places who wanted things, and everybody who lived in cities were like, well, I just go to Woolworths, so I go here. And there's this innovation of like, no, a large portion, 90% of our population is nowhere near there. Let's have this information that shows you here's 1,000 pages of what you can get. And the boost to our economy from that, just reorganizing the thought and the information of what's available dramatically changed, and it had such a huge impact. And I think what's the Mars version of that, and what, how does that apply? I can't imagine, because like you said, we're living with, my case, your case is 20th century minds trying to understand how people will adapt to problems that we can only think about conceptually.
Sure. Well, that's an interesting thought, because maybe the Sears robot catalog for Mars isn't a catalog of things that will be transported to Mars, but of programs for 3D printing whatever you need on Mars. Mm-hmm. So I'd like that. Well, okay, here's the program for it. Now you can go print it out.
Jumping back about 300 years from when we're colonizing Mars and making these new Sears robot catalogs, one of the things in your book that had never occurred to me before, Dr. Zubrin, was that we actually fund NASA more than we did during the moon landing. The kind of I read an article you wrote in National Review a couple of years ago that was talking about why the myths we tell ourselves for why we shouldn't have a specific overarching national goal for NASA, and one of them is, well, we don't fund it sufficiently, and proportionally that's true. It was NASA took up, I think, 4% of the if not the GDP, the tax
federal
expenditures.
Budget in 1966 in 1 year, yeah.
Right. So it was huge, because I think right now it's like 0.5% or something like that. It's much smaller. But at the same time, I had never thought about this before. The economy is much larger than it was in the 60s. The population is much larger. So even though the percentage of NASA's budget is smaller than it was in the 60s, it at the same time actually is funded in a constant dollar amount, factoring in inflation. We actually have more money for NASA than we did when we put people on the moon. So
slightly more, yeah. That is, in constant dollars, NASA has spent more in the past 20 years than it did in the first 20 years. That is from 1958 to 1978, during which time it did Mercury, Gemini, Apollo, Skylab, Mariner, Ranger, Surveyor, Pioneer, Jupiter, Voyager, and developed the full suite, or almost the full suite of technologies. Everything: hydrogen, oxygen, rocket engines, RTGs, multi-stage heavy lift launch vehicles, space rendezvous techniques, space navigation, communication, soft landing techniques, re-entry techniques, the whole bag of tricks. Did it all on. The budget right now, it's just a few percent more, but it's not less. It's not 1/10 as much or anything of the sort. It is slightly more. Now, if you break it down, what you find is that if you take those three areas, which include technology development, the robotic science missions, and human spaceflight, and compare the past 20 years to the first 20 years, what you find is in technology development and human spaceflight accomplishments, much lower level. If you look at science missions, it's comparable. That is, it's hard to measure our missions. They had more missions, but they were less capable missions. And of course, they were doing things the first time. But I think that NASA's record of science missions in the past 20 years, it can be held up against its record of science missions in its first 20 years and say, they're in the same ballpark. On the other hand, the accomplishments of the human spaceflight program do not remotely compare, and the accomplishments of technology development do not compare. Now, the reason, in my view, is because the science program today, like the science program then, and the manned mission program then, is purpose-driven. Okay, the human spaceflight program today is vendor-driven. That is, without a concrete and meaningful purpose, which it had during Apollo. Well, it was not a scientific purpose, but it was definitely a meaningful purpose. It was geostrategic, but still, it mattered what it was going to do. Okay, and so they were not doing things to spend money. They were spending money to do things, as is still true within the science program, the space telescopes, the Mars rovers, Cassini orbiters, and all this sort of thing. Those guys mean business, okay? But the human spaceflight program, without a clear direction, has become vendor-driven. It's become about who gets the money, which district, which contractors, and what's an excuse to keep spending money at the same rate as last year. And then the technology development program, without a clear objective driving the human program, there has not been the same incentive, better yet, imperative to take technology development to flight status. Because if you're not really doing things that are fundamentally new, as we were, of course, in the 60s, you don't need to develop anything new, and you can kind of piddle around.
Given that we have an unfocused and vendor-driven model right now at NASA, and that we have comparable funding rates to when it was doing all the heavy lifting in terms of human spaceflight, under the current budget, if we just reorganized it, could we get to Mars, or would we need a larger infusion of cash to achieve that?
If we had NASA being correctly run, we certainly could get to Mars within 10 years with the current budget.
Okay.
Let me, and not to sound ageist, but one of the things I've noticed, sort of sharp contrast, is NASA, like a lot of other institutions, the longer they are, sort of the bigger the management part of it grows. And like the median age of NASA is something like per employee there's like 50 versus during the Apollo era when it was like 30, or SpaceX where it's 30, and when you're that long in an organization, your roles shift and whatnot, and your organization tends to sort of represent that. Is that a factor?
Well, the age of organizations, so this is a general problem that affects not just government bureaucracies, but trade unions, political parties. You could go down the list. That originally they are established for a cause. And after a certain amount of time, whether the cause is accomplished or not, the fundamental purpose of the organization shifts to from being about the cause to being about the organization. Okay. And so, the kind of people who run the trade union movement today are very, very different from the kind of people that organized it in the first place. Okay. Completely different in character. And this is true in all sorts of political movements and as well. If you have the organizational culture as being purpose-driven or cause-driven, then the kind of people it will attract are those that are purpose-driven and cause-driven, which in many cases may tend to be younger people that still have the youthful fire in them, and to the extent it has older ones, it's older ones who still have the youthful fire in them.
Yeah, and I've noticed, and you would have more insight into this, that because there is, like the scientific missions and stuff, which I think we've done some exceptional stuff, where manned space flight is they're the victim of bureaucracies and senators and the whims of that. But with the rise of SpaceX, I've noticed there was a hostility that I saw some people from within NASA that I found, one, shocking, because I'm like, as Americans, I think they should be reading for this and thinking and assuming that all of them shared sort of the goals of science and cheaper payloads and, let billionaires, blow their money away trying to figure out these simple solutions. There was still this sort of like anger, this almost parochialism that just I found frustrating. And I think it softened a bit. But what's your thought on that? Well,
sure. Within sections of NASA that this threatened to show up, that is embarrassed. Obviously, they would be resentful, and certainly among competing contractors, the old guard. Well, initially they thought SpaceX was a joke, and then the joke wasn't funny anymore, and they tried to stop it. But there are parts of NASA, once again, as I say, the purpose-driven part. For instance, that have welcomed SpaceX. For instance, the Test Space Telescope was launched on a Falcon 9. And they could have launched it on a Delta IV if they had been willing to spend 4 times as much money on the launch. But a Delta IV could have done the job. But the Science Directorate doesn't feel that its purpose is to provide money to the Boeing Corporation. The Science Directorate, idea. Yeah. The Science Directorate feels that its purpose is to do science missions. And by saving $200 million on that launch, they got to spend it on other science programs. On the other hand, the purpose, of some of these programs, and they take the Lunar Orbit Space Station. Its purpose is to spend money. Or you look at most of the shuttle missions, not all. Some of the shuttle missions were spectacular, like the Hubble launch upgrade missions, so forth. That's 5 out of the 130. But if all 130 shuttle missions had been of that quality in terms of the results they produced, the shuttle would have been the greatest science program in human history. But and there's several other shuttle missions that you could point to that had important results. But the large majority of shuttle missions were flown simply to fly shuttle missions. And in other words, they were literally doing something in order to spend money. And so the space station was created primarily to give the shuttle a place to go. And the Lunar Orbit Space Station is being proposed for the purpose of giving Orion someplace to go. And before the Lunar Orbit Space Station, they had a different excuse for giving Orion someplace to go. This was the so-called asteroid redirect mission, which we'll put an asteroid in lunar orbit and we'll go visit it. And then they discovered they couldn't really put an asteroid in lunar orbit. And they said, well, can we go to lunar orbit and pretend there's an asteroid there? And someone said, well, that just is like too stupid. That's no one's going to go for that one. Okay. And so they said, well, we'll put a space station. Okay, that'll work. And we can go there and look out the window. And of course, the problem with the Lunar Orbit Space Station, as they're now finding out, they then attempted to justify it as part of a lunar mission architecture. They discovered it made the lunar missions more difficult. And so it has been removed from the critical path on the moon mission. They're now claiming, it's for Mars missions. Well, when the time comes when NASA actually wants to send humans to Mars, they won't send them to a lunar orbiting total. You may notice that SpaceX has no interest in building a lunar orbiting space station. Now, if NASA is paying them to deliver payloads to it, sure. But it's not part of their own plan.
So you mentioned SpaceX. Elon Musk has come up a couple of times in conversation. I've seen you reference him in articles before, Doctor. To what extent is Elon Musk's plan to get to Mars modeled after your own Mars Direct plan? And if they do differ, how so?
It has a significant heritage from Mars Direct, but it also differs in a number of significant respects. Okay, now the Mars Direct, as originally written, did use an expendable heavy lift launch vehicle. The SpaceX Starship is reusable, but we could certainly stage off of it, and it would still be the Mars Direct plan. SpaceX, Mars, significant features of Mars Direct was direct launch to Mars, no on-orbit assembly, landing on Mars with the same habitat craft that you'd fly to Mars in. In other words, there's not a mothership in Mars orbit and then a little landing craft. And direct return from the Martian surface using propellant, in particular methane oxygen propellant, produced on the surface of Mars out of local materials. So, and if you want to do direct return, you must do local propellant making. Otherwise, it's crazy. You'd have to bring too much mass and so forth. The way you get rid of that mothership and mission-critical Mars orbit rendezvous is by using in situ propellant. So in all those respects, it is the same. Now, what is different is that rather than stage off of Starship, he refuels the Starship and flies it all the way to Mars, and refuels it and flies it all the way back. Now, the advantage of that scenario is that it's fully reusable and there's only one flight element. The disadvantage is that it's a very large flight element, much bigger than is required. And so, for instance, the amount of propellant that you would need to make on Mars in the Musk plant is about 10 times as much as we need in Mars Direct. He also has to do orbital refueling, which you don't have to do in Mars Direct. Now, in the spirit of the Musk plan, which is full reusability, I came up with a kind of a modified Mars Direct in which the Starship delivers a mini Starship to Earth orbit, and which is fully fueled then it just stages off, it flies to Mars, and it can be refueled on Mars, and it flies home. So now you have a fully reusable architecture, but you got two flight elements, one of which is the mini Starship. And the mini Starship would be more or less sized to be like the Starship, but with a Falcon 9 as its first stage. So independently, it could be used as a fully reusable medium lift launch system. Now, I've discussed this with Musk, and he does not agree. He wants to only do one flight system. So I've been, in my career looking very much at the power and other requirements of in situ propellant production. He looks at flight system development. So I've been looking more at one aspect of the problem. He's been looking more at a different aspect of the problem. Now, I think that cutting the power and propellant making requirements on the surface of Mars by a factor of 10 is very much worth doing. He doesn't see that yet. But nevertheless, while we disagree on this issue, I like the way he is thinking in the following sense, that unlike NASA, who looks to develop anything they have any excuse to develop, his attitude is, show me why I need it. Okay, show me why I need it. Okay, and so he's looking for the minimum development path, whereas NASA looks for the maximum development path.
Something that I've been trying to wrap my head around is sort of the way he's thinking, which I think is interesting, is that he thinks that he can get the cost of the Starship, which would be the upper stage, down so low. Like he's talked like 10, 15 numbers that are less than Gulfstream jets, which just blow my mind. But his thinking is if that's the case, then putting all the materials he needs to do your idea of in situ propellant propulsion, et cetera, becomes much more feasible because he can put 10 of these things on the surface with all the equipment and have that 10x, fuel.
Right, that is his point of view. There's some issues there. I believe that if you can reuse the Starships rapidly, which he also argues, then why send it all the way to Mars and back when it's out of action for 1,000 days if you could just stage off of it and fly it again later that week? So there's a reduction of utility of the Starship. Then there is some question as to how cheap can you get it by mass producing it? Can you really get these things to cost $10 million each? Now his argument is once you're mass producing it, you can. That is that the reason why space launch vehicles are so expensive is because they're produced in ones and twos as opposed to in thousands like automobiles or something. It seems to me that there's no question that certain components of space launch vehicles like rocket engines, if you were producing them in thousands instead of ones or twos, could have their costs dropped from millions of dollars to tens of thousands of dollars because frankly, a rocket engine, even say a Raptor or something, is much less complex an item than a car, that you buy for $20,000. But one is, of course, mass-produced item, and the other isn't. But if he can get them very cheap, then his position starts to make sense. Although I think you could also get the smaller Starships very cheap, and they'd be more useful. I mean, how many people are going to be traveling back from Mars to Earth? Do we really need ships that house 100 people flying back from Mars to Earth? So it seems to me that having a certain amount of specialization here, if the Starships are cheap, by all means fly them one way from Earth to Mars, and now you've landed an apartment house on Mars. Okay, why fly it back to Earth with no one in it? Whereas the smaller Starships could be used as Earth return vehicles and return tens of people to Earth. So there's that. Now there's another issue, which is landing the Starships first of all, this idea of landing a starship on the moon, I do not think is credible. I think the plume that it would emit would dig a big crater on the moon, and I think there's a technical problem there. Mars, it's less of an issue. But once again, if you have the smaller starship, you could go there and you could build a landing pad of, that's paved over, and so you won't have a plume impingement plan if you do want to land big ones. And then finally, also, the starship, as currently designed, has a very lightweight thermal protection system. And it's one thing to take the heat load of coming back from Earth orbit. It's another thing to take it back coming from trans-Earth injection from either Mars or the moon. And so a starship that's designed to come back from Mars would need more serious thermal protection than one that's just coming back from Leo.
Guys, I'm going to actually cap it off there, as we've gone over about 30 minutes longer than I usually do on the podcast. And Dr. Zubrin, I apologize for taking up more time than I indicated in the email, but I was just so fascinated with literally every part of this, and I'm extremely grateful that you were so generous with your time to come on the show.
All right. Well, it's been my pleasure. And just, one last thing, if people want to read more about what I have to say, I've got 2 books. One's called The Case for Mars, and the other is The Case for Space.
I can't endorse those enough. Your thinking about all of this shaped so much of how I looked at what was possible at a time when I was feeling very depressed about where we were going in space, what was going. Reading you and how you were solving problems that were further out than our people thought to answer, but much more relevant and practical. Your research and institute, fuel development, all this sort of stuff was exciting and inspiring. So it's a pleasure to be here. And I just everybody should just pay attention to what you've been doing, because it's just part of the reason the dream is alive is because of you.
Oh, thanks.
100%. But thank you, Dr. Zubrin. And thank you, Andrew, for coming on and asking better questions than I would have.
I wouldn't say that, but thank you for having me.
Before we sign off today, I haven't quite got Mars out of my system, so I am going to read to you one of the best speeches ever written in human history. What I'd Say to the Martians by Jack Handey, from his excellent book of the same name. People of Mars, you say we are brutes and savages, but let me tell you one thing. If I could get loose from this cage you have me in, I would tear you guys a new Martian asshole. You say we are violent and barbaric, but has one of you come up to my cage and extended his hand? Because if he did, I would jerk it off and eat it right in front of him. That's good Martian, I would say. You say that your civilization is more advanced than ours, but who is really the more civilized one? You standing there watching this cage, or me with my pants down trying to urinate on you? You criticize our Earth religions, saying they have no relevance to the way we actually live. But think about this. If I could get my hands on that god of yours, I would grab his skinny neck and choke him until his big green head exploded. We are a warlike species, you claim, and you show me films of Earth battles to prove it. But I have seen all the films about 20 times. Get me some new films, or so help me, if I ever get out of here, I will empty my laser pistol into everyone I see, even pets. Speaking of films, I could show you some films. Films that portray a different, gentler side of Earth. And while you're watching the films, I'd sort of slip away, because guess what? The projector is actually a thing that shoots out spinning blades, and you fell for it. Well, maybe not now, you wouldn't. You point to your long tradition of living peacefully with Earth. But you know what I point to? Your stupid heads. You say there is much your civilization could teach ours, but perhaps there is something that I could teach you. Namely, how to scream like a parrot when I put your big Martian head in a vice. You claim there are other intelligent beings in the galaxy besides Earthlings and Martians. Good. Then we can attack them together. And after we're through attacking them, we'll attack you. I came here in peace, seeking gold and slaves. But you have treated me like an intruder. Maybe it is not me who is the intruder, but you. No, not me. You, stupid. You keep my body imprisoned in this cage, but I am able to transport my mind to a place far away, a happier place, where I use Martian heads for batting practice. I admit that sometimes I think we are not so different after all. When you see one of your old ones trip and fall down, do you not point and laugh, just as we on Earth do? And I think we can agree that nothing is more admired by the people of Earth and Mars alike than a fine, high-quality cigarette. For fun, we humans like to ski down mountains covered with snow. You like to milk bacteria off scum hills and pack them into your gill slits. Are we so different? Of course we are, and you will be even more different if I ever finish my homemade flamethrower. You may kill me, either on purpose or by not making sure that all of the surfaces in my cage are safe to lick. But you can't kill an idea, and that idea is me chasing you with a big wooden mallet. You say you will release me only if I sign a statement saying that I will not attack you, and I have agreed. The only condition being that I can sign with a long, sharp pen. And still, you keep me locked up. True, you have allowed me reading material, not the human reproduction magazines I requested, but the works of your greatest philosopher, Xandor or Xanax, or whatever his name is. I would like to discuss his ideas with him. Just me, him, and one of his big, heavy books. If you will not free me, at least deliver a message to Earth. Send my love to my wife, and also to my girlfriend. And to my children, if I have any place. Ask my wife to please send me a bazooka, which is a flower we have on Earth. If my so-called friend Don asks you where the money I owe him is, please anally probe him. Do that anyway. If you keep me imprisoned long enough, eventually, I will die. Because one thing you Martians do not understand is that we humans cannot live without our freedom. So if you see me lying, lifeless in my cage, come on in, because I'm dead. Really. Maybe one day, we will not be the enemies you make us out to be. Perhaps one day a little Earth child will sit down to play with a little Martian child or larva or whatever they are. But after a while, guess what happens? The little Martian tries to eat the Earth child. But guess what the Earth child has? A gun. You weren't expecting that, were you? And now the Martian child is running away as fast as he can. Run, little Martian baby, run! I would like to thank everyone for coming to my cage tonight to hear my speech. Donations will be gratefully accepted. No Mars money, please. That's the show. Thanks for listening. Thank you, Robert Zubrin and Andrew Mayne, for some fantastic guesting. Thank you, Jack Handy, for writing a truly brilliant speech. We'll see you next week. Until then, tally-ho!